In today's session, I'm going to teach you the concept called random forest. So I'm going to teach you the coding related to random forest in the next video. So as a forest is made of trees, similarly, random forest is also made of decision trees. Decision tree searches for the best feature while splitting a node. Random forest search for the best feature among random subset of feature. So this will result in a high diversity and gives better results. And decision random forest is a supervised learning model. So what we were doing in decision tree is that we were trying to find the best feature for doing the splitting, right? So if you have watched my previous video, you are trying to find the best feature that gives uh, high Gini, okay, high Gini value or high information gain value. So there is less impurity. So we were trying to find high purity. Okay, so that is why we were trying to find the best feature with the feature which gives the feature which gives high accuracy for our problems, classification problem. So when you consider random forest, this is not only about trying to find the best feature. This is to trying to find the features among subset of features. Okay, so this is about random forest. So it is a form of supervised learning model. So we have in random forest, we have ensemble model and ensemble implies combination. So let me teach you brief about this. So ensemble means a technique of combining multiple decision tree either parallelly or sequentially results in an ensemble model. So in ensemble, we have bagging or bootstrap, then we have boosting. So let me go to this PDF. So in Ensemble, we have seen that tagging or bootstrap aggregation. So let me tell you what happens in that. So you have a data set having m rows and n columns. So let's say we have a data set with 500 records and 16 features. Okay, so 500 records means rows and 16 features in 16th column. So what you will have to do is that you will create multiple decision tree for these features, for these records and features. So how we are going to choose the number of records you want? So M is 2 by 3 of total number of records. So 2 by 3 of 500 is, it's almost 500. If I have 500 into 2 by 3000 divided by 3, it almost comes around 330. So can I have a value around 350, okay? 350, 300, like that value you can have. So the sample decision tree the decision tree that you are going to create for this big data set is like you have to take a sample of m rows and in columns. So m rows will be in the form of 2 by 3 of m, and n rows, n columns and features will be square root of number of features. So now we have to draw the decision tree. You have to build a decision tree for this m rows and n rows and n features, and you similarly you will do sampling with replacement. Okay, so you have taken some records from here and some features, and you have built a decision tree for that. Then once again take the same sample and then take the same population and build sample. Okay, so build sample with replacement, okay, with replacement. So once you have used all the records and features, then you have put it back and you will use, and now we will create a new decision tree with m rows and n columns or m records and n features. Like now we will take 380 and this is replacement. Okay, once you take that 380 and five features and then you build the second decision tree, then you put it back and once again you try to take 370 rows and six features from this population data set. Okay, so what you're doing is that you are building decision tree for each sample that you are taking, that is sampling with replacement. Okay, so once you have done that, so let me go to the theoretical part over here, how it works. Okay, so ensemble models I have shown you. So this is ensemble models. We have bootstrap, aggregate, bootstrap or bagging or boosting, sequential. So this is a bagging method that we are considering, and this happens parallelly. Okay? Parallelly, we are creating decision tree over here. And once you create decision tree parallelly with some samples, then what you will do, then let's see. Suppose a data set has m rows and n columns. So there would be a total of m cross n elements in this data set. Okay, this I have explained. For this, multiple decision tree can be created from the sub data set of size M1 cross N1. Okay, so you can create multiple decision tree of subset of sub data set of size M1 cross N1, M2 cross N2, and so on, where M is less than M or M is almost equal to 2 by 3 times of M, and N is almost equal to square root of M. We have seen this one as well. Note, in the selection of decision tree, sampling is done with replacement. So that's what I have explained before. So this is how you are going to create decision trees from a main data set. So main data set you will take, and then you will take the sample data set from the main data set, and then you'll create decision tree. So this exact process of bagging happens in a random forest machine learning. Okay. This is what happens in a banging method in random forest machine learning model. So the random forest, as the name suggests, is combination of multiple trees. Okay. So this is combination of multiple decision trees. For random forest, bagging is ensemble technique used. Okay. So ensemble technique used here is bagging. Okay. Bagging. This is bagging method because it happens parallel combination. So benefits of bagging is the result of all the decision tree are combined. So whatever decision you get from here, 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 you combine that. The voting technique is used to decide the final class. The final class is nothing but the output class. So you will all combine this. Let me show you. So you will see good, bad, bad, good, bad, bad, good, bad. So you'll all combine this decision tree and predict the final class. Okay, this is how you will do the decision tree ensemble model bagging method. Okay, so this is how. So this increases the predictive power as accuracy does not depend only on one decision tree. So this is the main advantage of having random forest. So accuracy just doesn't depend on the one decision tree since we have multiple decision tree. Based on that accuracy of multiple decision tree, the output of the final class will be decided. Okay, as it is not only dependent on one decision tree. So this is all about bagging method. So then we have a boosting. Boosting is nothing but a series combination. So let me explain what's boosting here. So boosting is an ensemble technique that works sequentially. So we have seen that in ensemble we have two techniques, bagging, or also known as bootstrap, and boosting. So in boosting is an ensemble technique that works sequentially. Let me show you that. So you could see that this is a sequential. So so the output of the first decision tree is used to alter the approach of the second decision tree. Okay, then the output of the second decision tree is used to decide the approach for the third decision tree. This is how a sequential boosting method works. And in the same format, sequential decision trees are creating, improving the process at every point. So what is boosting method is doing is that, so the output of whatever you are getting, the first decision tree is actually feed it to the decision tree, second decision tree, and making the decision to alter, so it can make a good decision from the second decision tree. That is the output of second decision tree used to decide the approach for the third decision tree for next. So this output will decide the approach. Okay, first decision tree approach will be helping to decide the approach for the second decision tree. The first decision tree output will help to decide the approach for second decision tree. The output of decision tree 2 will decide the approach for the third decision tree. Okay. So, and in the same format, sequential decision tree are creating, improving the process at every point. So here also the same, like how we create decision tree. So m is less than m and n is less than n. So we take m value is 2 by 3 of m and n is 2 by root square root of. So and in the same format, sequential decision tree creating. So now, so let me take you through an example. Okay, suppose we have n features, and the output says if a person is a strong learner or weak learner. So that is clear. Correct. Strong learners are correct classification, whereas weak learners are incorrect classification. Let's say that. Okay. So output is yes, he's a strong learner. No, he's a strong learner. No, he's not a strong learner. It's like that. Okay. So now let's say the weight of each individual. So we have 10 records. So each individual corresponds to 1 by 10th of the weight. Okay. So 1 by 10, 1 by 10. So we see that this is an incorrect classification. Okay. He was told that this guy is weak learner. So this one is incorrect classification. So number of samples, number of records we have is 10, and initial weight for this first record is 1 by 10. 1 by n is 1 by 10. So what happens is that when you create a decision tree, then you will understand that there are 9 strong learners and 1 weak learner. Okay. So what's the error? So the error is here is the classification of a weak learner. So total error is sum of all the sample weight of weak learner. That is 1 by 10. So, okay. One classified as weak learner. This weak learner is incorrectly classified. Let's say. So performance of the stamp, this is the formula 1 by 2 log to the base e of 1 minus total error by total error. So apply it on this formula, this value 1 by 10, so you'll get an answer. So what happens is that as weight of incorrect classification rows is weak learner increases, weight of strong learners is correct classification rows decreases. Okay. So this is how it happens. So new sample weight for a incorrect weak learners is W new is W old into the E power performance. Okay. So as the value is increasing for this E power performance, so the weak learners value is also increase. So as the performance increases over here for strong learners, then strong learners value gets decreases. Okay. So we will continue with the random forest uh, theoretical part. So forest is made of trees and random forest is made of decision trees. Okay. And ensemble model training helps with bagging method. Okay. So bagging we will use. So what makes it different? So combination of learning model because we are combining many decision trees over here. So based on that decision trees combination, we will be predicting our output class. So that is the difference here because in decision tree we used to take only one decision. We used to create only one decision and make a prediction on that for our classification problems. But here we'll create multiple decision tree and based on those features, we will make those features and those decision trees that we have created will predict the output class. So random sampling happens with replacement here, decision tree. So that's one thing which is good. So what is decision tree? Let's see. So decision tree searches for the best feature while splitting the node, whereas random forest searches for the best features among the random subset of features. Okay, this is what's the difference between so decision tree searches for best feature while splitting. Random forest searches for the best feature among one subset of features. So results is high diversity. So when you're solving a decision tree or classification problems using decision tree random forest, so the internal calculation that's happening in the random forest is not able to find out. So you will definitely get a high accuracy when you are applying random forest, but the mathematics behind that you won't be able to understand because it's like one of the algorithms which is hard to understand because it's happening inside in the back end it's happening so that is one thing actually people usually not go with random forest but yes if you have a training data set and you know that your testing data set will be a subset of training data set It's better to go with decision tree because it will give accuracy, good accuracy. But if you know that your testing subset won't be testing data won't be a subset of that training data set, and there can be some of the data that are not there in training data set, so which are exposed. Okay, if data set is not exposed to training data set, then I would suggest you to build a model using random forest, because it will give a high accuracy in these cases. So let's see cross validation. So before going to class cross validation, okay, in jobs, okay. So let's see cross validation first. Okay. So we have a k-fold CV. This is k-fold cross validation. Okay. So let's say you have a data set. So first, what you have to do is that, so you have a population data set. First, divide the data set into k groups. So let's take an example here. So I have a data set. I've divided the data set into 10 parts, 10 groups. Okay. So take one group as test set. So I'm taking the 10th group as test set. Remaining k minus one group as training test. So I'm going to train my model using these set. Okay. So fit on the training set and evaluate. So train the model using this training set, and evaluation is done on test. Repeat till all the groups are used for both training and testing. So next time what I will do is that next time I will take 9 as the training testing set, and 1 to 8 and including 10 as the training set. Okay. Next time, similarly, 8 you will take as training set, testing set. And next time, once this is done, then I will take 7 as the testing set. So repeat till all the K groups are used for both training. So all the groups has been used for testing and training as well. So make sure that. So once you've done that, apply evaluation matrix. So after applying evaluation matrix, you could see, so this will give better results. Okay. So we could see the parameter, hyperparameter, that we call it hyperparameter. So which hyperparameters, I mean, I mean, we can't go is really go with the hyperparameter thing here. So, but when you apply evaluation matrix, you will understand, you can see which is giving the good results. Okay. So this is how you do. So training set 29, testing set 10, training set 28 and 10, testing set 9, training would set 1 to 10, 9, 7 and 9 and 10, testing set 8. So this is how you do cross validation you have to do. Cross validation is nothing much, just doing the tuning. Okay. So let's see hyperparameter tuning. So before going that hyperparameter tuning, let's see overfitting and underfitting problems. So, and also I wanted to mention that cross validation is nothing but it means how many fold of cross validation we are giving. Okay. Here we are giving 10. So you can give 10 based on your requirement. So the evaluation matrix we are using here is the confusion matrix. It's a table that is used for defining the performance of the classification algorithm. So now let's go for comparison between overfitting and underfitting. This is one of a concept that you must understand while dealing with machine learning problems. So overfitting occurs when a model or algorithm captures the noise in the data. That is, intuitively, it occurs when your model fits the data too well. So good accuracy for training set, but poor accuracy for testing set. So overfitting usually happens when you have exposed all of your data for training. Okay. Then only overfitting happens. That is mostly when you have 100% accuracy on training data, and you have less accuracy on the testing. Then that kind of thing will be causing overfitting. Like let's say you have 100% training accuracy and 90% testing accuracy. That is the overfitting. Okay. And overfitting is just like you are making the model to remember. Okay, so that is like more model is not learning. Instead, your model is remembering. Okay? That's the problem with overfitting. So when it comes to underfitting, occurs when a model cannot capture the underlying trend of data. So if your model hasn't got the enough data set to be trained, then there is a chance that the model has not captured the trend. Okay, so your model should get enough data for it to get trained in such a way that it can give accurate results for training data set. Once you get accurate results for training data set, you can actually do the evaluation or check the accuracy for the testing data set as well. So usually underfitting occurs when the model hasn't got enough data for training. Okay. And here in underfitting, accuracy is less. So you can see here for overfitting, the model is trying to draw a curve kind of thing where it is trying to fit all the points in your data set. So this is the overfitting problem. Whereas here your model is has drawn a line, but most of the points doesn't lie on that. It is lie outside those this kind of line that we have drawn. Okay. So now let's come to the next concept called hyperparameter tuning. So in hyperparameter tuning, in a model, there are some parameters that are calculated by models. So hyperparameter tuning, what happens is that it's like trial and error. Okay. So the machine itself is doing the trial and error inside and trying to find the best features and best method to get high accuracy on your training as well as your testing data. So let me explain that. In a model, there are some parameters that are calculated by models. Okay? And there are some parameters that can be controlled manually. These set of parameters are called hyperparameters. So let me explain. So some parameters are there like max depth, minimum sample sleeve, max features, number of estimators, minimum sample split, and end jobs. Okay. These are the parameters that are present in your model, and you can manipulate it by these features manually. You can manipulate these parameters manually, or the machine can take care of it itself if you put it on auto mode. Okay. So what we'll do in auto mode, the machine will actually try to find the best parameters values, and it will try to find once it find out the best parameters that will give the high accurate results. So you can use those parameters values to your model. Okay, so let me show you the more example related to that. Once the model is selected, it can be fine tuned by altering some of hyperparameters. So in previous decades, you used to see radios, right? So they used to tune it in a such a way that you get to listen music, news channels, or some kind of entertainment channels as well. So why they what they were doing is that they were trying to tune it in such a frequency that it will catch that particular frequency so that you can see, you can listen to cricket, or you can listen to music, or you can listen to news channels like that kind of thing. So at particular frequency level in the radio, you would be able to listen to this because that whatever was broadcasted during that using that channel frequency. So you had to tune that frequency. Like this is here also, this is how we do fine tune. So once the model is selected, it can be fine tuned by altering some of the parameters. So we are trying to alter some of the hyperparameters so we can get a fine tuned model. This allows to checking for which hyperparameter values model generated accuracy. So this is what we are trying to find out. The hyperparameters model, hyperparameters that is helping us to build a high accuracy model, that those parameters we are trying to find out. Examples of hyperparameter is maximum features to include in a node, minimum samples in a leaf load, maximum features We have seen maximum features to include in a node, minimum samples in a leaf node. So we have seen decision trees. In that, we have seen maximum features to include, minimum samples in a leaf to be there, and maximum depth, that is height, maximum depth that we need to share use, number of estimation, minimum sample split we want, and then jobs. So these hyperparameters affect the performance of the model. Okay, N jobs are hyperparameters that control the speed of the model. So we have seen that hyperparameters affect the performance of the model. So N jobs are what is used to control the speed of the model. It helps the model to know how many jobs can be done simultaneously. So let's take an example. Okay, so N jobs is equal to one, which implies one job must be done at a time. It's like one processor we will assign for that. Okay, N jobs is three, which implies three jobs can be done simultaneously. It means three processor we will assign. So if we pass N jobs is -1, all processor will be used. That is, there is no limit on the number of tasks that can be done. So this is all about hyperparameter tuning. Okay, so let's now come to the grid search CV. So grid search CV is a model selection package. So why we need? It's a manual, uh, time consuming process. Okay, so I had told you hyperparameter where we had said that it can be done manually or automated. So grid search CV is used for model selection package. So not keep track of hyperparameter. Okay. So what we will do in grid search CV is that inside that we will pass number of features, depths, number of depths, and number of jobs will pass, and we will also pass number of leaves. So your grid search CV method will try to find out the best value from each of the parameters. Okay, if so, you have passed a subset of values over here. A set of values you would have passed for each of the features. And your grid search CV is a model selection package. It will select values in such a way that your model will have higher accuracy. So so it will check for each value, and it will return a parameters values which are giving high accuracy. So you will use that parameter values for your model building. Okay. So let's see when to use this. So when you want your model to be simple and explainable, so decision tree is easy to explain and it's simple model. So when you want non-parametric model, okay, there is no parameters that are present in our model, then you can definitely go with decision tree. Since it is like you have to mention the criterion is Gini or entropy kind of thing, and you just have to mention maximum depth. Okay, when you don't want to worry about feature selection or regularization or worry about multicollinearity. So, so when can you use is that when you don't want to worry about feature selection or regularization, then you can go with decision tree. And also, if the multicollinearity concept doesn't come, decision tree. Okay? So you can overfit the tree and build a model. So multicollinearity doesn't come here because you are trying to find out the best thing. Okay, so you will get most of the time you'll be able to find a feature among features that are present in your data. Okay, so you can overfit the tree and build a model. If you're sure the validation or test data set is going to be a subset of training data set, that's what I said previously as well. So if you know that the test data set will be a subset of training data set, and you won't be won't be using other data set that are not that model has been trained. I mean, when you know that the validation test data set is a subset of training data set, or almost overlapping instead of unexpected. Then also you can go with decision tree. So if you're sure that there won't be any unexpected values that are present, so that can affect your model. So, and you know that the validation test is almost a subset of training data set, then you definitely go with decision tree. So let's see when to use random forest. So when you don't bother much about interpreting the model, but want better accuracy. Okay. So here the interpretation cannot be done, but you will get high accuracy because it's creating multiple decision tree parallelly using bagging method, and it's trying to find out the output class based on the combination of decision trees. Okay, so here you won't be able to interpret the model. So random forest will reduce the variance part of error rather than the bias part. So on a given training data set, decision tree may be more accurate, okay, than random forest. So training data set, a decision tree might be more accurate on the random forest, but on an unexpected validation data set, random forest always wins in terms of accuracy. That's what I was saying. If you know that your subset, the data set, training data set, and testing data, the testing data set is a subset of training data set, then you can easily go with the decision tree. But you're sure, if you're sure that there can be unexpected validation data set that can come, so always go with random forest because it always wins over decision tree in comparison with the accuracy part. So this is all about the random forest classification problem I was teaching. So I will be teaching you the coding part related to random forest. Let's see hyperparameter tuning and cross validation and so on, regularization and concept of lagging and boosting. So let's see those concepts in the next video. Thank you for attending the session.